hi, this is a bonus, a bit like an Easter egg, okay? You don't really need it, okay? You bought the DVD or the Blu-ray or whatever, that's your thing. You don't really need it, it wasn't what you bought it for, okay? But it's there and you think, oh, may as well watch. It's just a little bonus, okay? Right, so this is the trapezium wall, yeah? And what I'm going to do is I'm going to change it a little bit, okay? Instead of calling the width of each of these strips H, I'm going to call it delta X. Woohoo, it's going to be exciting, isn't it? Because delta X is what we often use to represent a small change. And you've seen delta X before. Now hopefully your mind is thinking, oh gosh, where did I see delta X before? Oh no, oh god, it's the principles thing, the differentiation first principles. Yeah, exactly right. Okay, but I'm going to just change it slightly, okay? And for that I'm just going to get rid of this, okay? And how's this going to change? Okay, well, I'm going to change that slightly, okay? I'm just going to change it. Well, let's just rub the whole thing off, shall we? Yay! Let's just rub the whole thing off. Okay. What we've got is, effectively, we've got area of each of these trapeziums, delta X. Now, what happens as we have an infinite number of strips? Okay, this is not a strict proof, so please do not post this as Mr. Brown's strict proof, because I'll get slated by the mathematical community. I don't know who the mathematical community are, but I don't like the idea of being slated, okay? Infinite number of strips, okay? What does that imply if you've got an infinite number of strips, okay? Well, it implies really you don't have trapezia anymore, okay? You've just got lots of straight lines, okay? Let me just try and illustrate that by drawing in lots of straight lines, okay? As if you don't need to know. So it's like this, isn't it? There we go. Oh, I'll keep on going forever, won't I? Yeah, that's what infinity is about, isn't it? Yeah, I'll be going on forever. But it would fill this area perfectly, lots of straight lines, wouldn't it? Okay. What am I doing then? Okay, I'm adding y0 plus y1 plus y2 plus y3 plus y4, okay, multiplied by delta x. Effectively, they are almost like rectangles, okay. As the width of this becomes smaller and smaller, as the number of strips tends towards infinity, delta x is tend towards 0, effectively, okay? So an infinite number of strips, and also what we're going to have is delta x is going to tend towards 0. Remember that, there's a bit of that with principles, you know. We had h tend towards 0 in some cases, but delta x is what we often use. Delta x works out nice for this example, okay? But we've got an infinite summation here, haven't we? I'm going to write that using this, okay? Opportunity to get sigma in there somewhere, okay? Yeah, so between x equals a and x equals b, okay? Well, effectively what we're doing is we're multiplying all of the lengths, the heights, by the thickness, okay? Done with trapezia now, okay? We haven't got an infinite number of them, it's pretty much like a rectangle each, okay? And what's the area of a rectangle? Yeah, it's each one of these y values times by delta x, isn't it? Well, the y values can be given algebraically as just y. The y value, it's more of a generic term, the y coordinate, okay? And each of these x values, what's that? Delta x. What's coming up next? Okay. Well, if I can just squeeze it in, and I'll put in a limit there, as delta x tends towards 0. This here, this tends towards something very interesting. Do you know what we use instead of the Greek letter sigma for when we're dealing with limits? We still use an s, but we make it an elongated s. One of those. This is what you call a wow moment in mathematics, okay, if you've not seen this before. This is like, suddenly all of this calculus integration makes sense, okay? Are you feeling it? I really hope so, okay? It's a good Easter egg, isn't it? And it's nearly Easter, woohoo! Look how that worked out. And the limits I'm using are between a and b, and it's the integral of y. And instead of delta x, what do we use when we've got limits and delta x tending towards 0? You've got it. We use d instead of delta, we got dx. Integration and y, it gives us the area underneath the curve. Okay. Hope you enjoyed that. Okay, hope that was good for you. Worth watching at least one more time today, I would say. Yeah. See you later.